Alright, here we are in section 5.2, and we're going to remind you about inverse functions, also something that you would have needed to talk about in an Algebra 2 setting as you talked about exponential and log functions. Certainly something you would need to talk about in trig, as we have the inverse functions of arcsine and arccosine that are needed for us in order to solve a lot of trig equations and also applications. And so I know you're familiar with inverse functions, so let's remind you that about inverse functions. So a function, let me take a black pen there, sorry, and come in here, apologize for that. Just back up over that. So a function has an inverse function only if it is one-to-one. So remember what one-to-one is. A one-to-one function assigns every x input a unique y output. Okay, so let's talk about some functions. Here's a function that we know well, right? We worked with it, the x squared function. The x squared function is not one-to-one and therefore does not have an inverse on its entire domain. So we'll talk about that as time goes on. They have the two examples that I grabbed out of here because there's not much that needs to be shown here. Just a reminder of how to find inverse functions and what they are. So what we want to remind you is that they have to be one-to-one. So it's impossible to back everything out here in a function relationship. And here's the reason why. What's f of 2? Well, f of 2 is 4. What's f of negative 2? Well, that's also 4. So that's a problem because this second 4 is not a unique y output. There's 2 that are going there. And so remember, if we were to set up an x, y, right, with the f of x going this way, it would send both 2 and negative 2 to the exact same value 4. Now, that's a function, no problem, if you look at f of x, but if you try to reverse it, we got big issues, because what an inverse function does is take y values and sends them to x's, right? So your inputs are now your y's and your outputs are now your x's. Well, I have the same input of 4 going to two different outputs, not a function. That's why only a one-to-one function can have an inverse function. So how do we fix that? Well, we limit the domain of f of x equals x squared. Remember what it looks like. The f of x equals x squared looks like this. If we were to draw a horizontal line, if that horizontal line touches in two places, the function is not one-to-one. And so this is not a one-to-one function because what that line represents is possibly like the output of 4. There's two values, 2 and negative 2, that are being sent there. It could represent 9, 3 and negative 3 are being sent there. And so there's lots of violations in that. So not every function we've dealt with is one-to-one. Many are. If you consider f of x equals x cubed, you know what that looks like. It's kind of like our tangent function, but it's this snake-looking guy. Take a look at that function. Does it pass a horizontal line test? Absolutely. If we were to draw horizontal lines in there, they would cross in only one place. What's f of negative 1? I'll stick with the same ones. F of negative 2? Well, it's negative 8. And f of 2 is 8. They're two different values. And we back up and can get to that guy. And you know what the inverse function is. The inverse function for this is the cubed root of x. That's what would back it straight out. Now the problem with this one is if you say, oh, well, this one had an inverse as well. Its inverse would have been the square root. This square root function will never, ever give you the negative portion of it. And so the problem is you'll only be mapping to half the original domain. So what happens with inverse functions too is if the function f of x, if that function is going from a domain in f of x is sending it to its range. What happens for the inverse function, which I'll put in red, is the inverse function goes the other way. That means the range elements for f of x are a new domain, and it has to map into the range, right, which is the original domain. So that's the problem with this first one, is if I look at this function, it will never map back to this part of the range. And so they have ways to fix that. So I just want to remind you about that. So what are the questions you're going to see? The questions you're going to see are to find f inverse of x when given something. And they're pretty standard what they give you, just practicing finding that. But I'll remind you what we do. So I'm going to look, I'm just trying to debate which one to do first. I'm going to do, for my first one, f of x is equal to 9 over 5 plus x. Right? And that's for all x not equal to negative 5. Let me make that plus look a little bit better in there. It's bothering me. Sorry about that. First I saw it as a minus, but I do see it's a plus that they had there. Okay, so x can't be negative 5. So the domain of this thing is all reals except negative 5. Let's go find f inverse. So how do we find f inverse? No problem. Remember what you did back in intermediate algebra that you'll continue to do today, and that is you interchange the roles of x and y. So to get the inverse function, you let f of x, which is traditionally y, be x, and I'm going to leave the other, well, I'll put it all in blue, is equal to 9 over 5 plus y. And you solve for y. So you know how to solve for y. We've got to get it up out of the bottom, so we're going to multiply both sides by 5 plus y. Okay, and so what do we have? We have 5 plus y times x is equal to 9. Well, we're after that y, so we got to distribute that x. That's 5x plus yx is equal to 9. That's yx is equal to 9 minus 5x, and that's y is equal to 9 minus 5x all over x. Perfect. So what's y equal to? Well, y is now f inverse of x. So we need to always relate it back to the f function. So I think they'll actually put f inverse of x in the homework, but if you didn't write it, that would be a problem. We definitely want to relate it back in its relationship to that. So they want to know something. They'll want you to find it. No problem, we got it. And now we want to find the domain. So the domain, let's just look at this guy. What's its domain? It's the set of all reals except 0. So it's the set of all x such that x does not equal 0. You can just see that. Any other x would be fine for f inverse of x. What's the range? Well, the range might be hard for you to think about and see, but honestly what it is, it's the domain of f. The range has to be the set of all x such that x does not equal negative 5. Now, let's make sure you understand why. So that's what theoretically should happen. Hopefully you see that. So how did I come up with the range? I came up with the range by the domain of f of x. It has to be that, because this relationship has to hold true, that the domain of one is the range of the other. Now, how did I get x not equal to 0? I looked at the domain of this function, right? I just physically said what's going to make the bottom 0. Oh, 0 is going to make the bottom 0. Okay, and so we have the domain and the range. Now let's make sure that we understand why. We know what this graph looks like. Let's go look at the graph of f of x and talk about it a little bit. Let me switch to black. What will this thing look like? Well, x can't be negative 5. So we got this line right here. Has no zeros. And what do we know from our previous study? So you're like, why do I have to do all that other stuff? Well, you know that this thing, the degree of the bottom is bigger than the top, so you know it has a horizontal asymptote that it cannot cross at 0. It's never going to be 0. Okay, you know that the multiplicity of the negative 5 is 1, so it's going to be on one side and the other. So let's pick a number that's bigger than negative 5. Let's pick something like negative 4. Well, I'm going to be positive. And so we're going to look just like this, and we know it's going to go to the other side. So we know this is what that function looks like. Well, take a look at its range. Its range is all reals except 0, the exact domain that we picked here. So it's working out perfectly. And the fact that we can have these mental images of what these rational functions look like is super helpful. So you can start to get an idea of why we cared so much about those later sections in chapter 4. Actually, weren't the later sections, they were towards the beginning. Another problem that could happen is something like this. Now, take a look at this function. F of x is equal to x squared minus 1. It's that x squared function which I claimed was not 1 to 1. Well, they're not going to look at the whole thing. They're going to look only on the region of x being greater than or equal to 0. Well, what does that look like? Well, you know about this from an earlier chapter. This is the regular parabola shifted down 1 unit, and you're only looking at the positive half. Only looking at x being greater than 0. You're not even getting that left-hand side. That's totally 1 to 1. We can find its inverse. Okay, so let's go find its inverse. Its inverse is, well, we know what to do. I'll go back to blue. We take our f of x, which is y, and make it an x. Our x, y squared minus 1. We solve for y by moving over the 1 and taking the square root of both sides, and get y is equal to the square root of x plus 1. Now we're going to deliberately choose the positive square root in all of that because of the shape of this guy. Okay, we're definitely going to choose that because it's going up. Because of the outputs all over here being on the positive side of 0. If it was on the negative side of 0, we'd have to choose the negative one. But so that's what we're choosing, is this function right here. That's the function. So let's talk about its domain. Just look at it. You can tell me what the domain was. You could tell me what it was earlier in this class. You could tell me what it was in intermediate algebra, probably even beginning algebra. I think we solved square root equations and had to talk about domain. You know that this is going to be the set of all x that is from negative 1, and it can be negative 1, all the way up. Okay. The domain is from negative 1 to infinity. What's the range? The range is going to be the domain of the original function, 0 to infinity. Okay. Now let's take a look. Does that make sense? The range, the domain of this function, the domain of the inverse, should be the range of the original. Well, the range is from negative 1 to infinity. You can see it there. It drops down to a low value of negative 1 and goes as high as we want. And why did we know the range was 0 to infinity? We just took it for granted because it should be that. But you know what this function looks like? You know what the square root function is. That's why we had you do the parent graph, so you'd understand these guys. Hey, this is the square root graph moved 1 unit to the right. Or sorry, 1 unit to the left. I said that wrong, drew it right, but said it wrong. And looks like that. That's what my graph is. So what's my domain? Of course it's negative 1 to infinity. What's my range? Of course it's 0 to infinity. I don't even need to rely upon that as long as I know my parent graphs. And so all these things that you thought were these compartmentalized little things, and why am I doing this? They all come together to build understanding of larger concepts so that you can say, oh, I can see why they're saying that has to happen. That's when real understanding happens, and that's what we're trying to teach you here.